All right, so in this chapter, we're going to start looking at the gases, and you can see at the bottom here, different sort of sections that we're going to focus on. So in this video, we're essentially just going to kind of give an overview of gases, talking about pressure and things like that. And then in the later ones, you can see we'll start to look at the relationship between different factors, so pressure, volume, amount of gas, temperature, things like that. And then, of course, we'll be relating this to chemical reactions involving gas, and then ultimately looking at the behavior of gases. And with this chapter, might be a little bit more kind of directly applicable to your life than some of the previous ones. You can see here the hot air balloons. So those are going to, of course, be filled with gas, and we're going to see why or how we can kind of make those work in terms of like why they're flat on the ground here. But when we heat them up, we get the balloon to then rise. So we'll see that as we go through these different sections. And when we're thinking about gases, we can't see them, obviously, or at least for the most part, we can't see them. But we're going to be surrounded by them constantly. So when we're thinking about the air we're breathing in, gases, of course, the entire atmosphere. And with the atmosphere, if you take like meteorology or maybe astronomy, something like that, you'll go into the different kind of layers of the atmosphere, so mesosphere, stratosphere, ionosphere, things like that. But with it, we're just kind of looking at the gases that are going to be within those layers. And within the atmosphere of Earth, there's going to be two main components. So nitrogen going to be about 80%, a little bit under. Oxygen typically going to be a little bit over 20%. So if we think about that combining for 99, and then with the remaining 1%, we're just going to see a whole bunch of trace gases, really. And then most of that even is going to be argon here. So carbon dioxide, excuse me, obviously a big factor in global warming, but it's going to be a very, very small component of the atmosphere. It's just going to be able to reflect some of the, or absorb some of the reflected sunlight from the Earth's surface and retain some of that heat. And with methane right below it, going to see the same thing. So you can see carbon dioxide is a larger component of the atmosphere than methane is. And that's typically why we focus on carbon dioxide when we talk about global warming, especially because carbon dioxide is the substance that we're producing in such large quantities. So you can see about 2 orders of magnitude and a little bit more than 2 orders of magnitude difference here between these. So like I said, because we produce carbon dioxide in such large quantities is why we tend to focus on it in terms of the global warming and some of the methods that we're trying to develop. Of course, legislation, different policies to curb those types of carbon emissions. But in terms of methane versus carbon dioxide, if we had both of those in equal quantities in the atmosphere, methane would actually be the worst substance in terms of global warming, just because it's going to have what's known as a higher global warming potential. So just when it absorbs that energy, it's going to keep more of that heat in, essentially. And then with this, also just note, you don't see water anywhere here. But of course, if we're thinking about humidity, water is going to be a big part of the atmosphere in that case, or at least the local atmosphere. So with these percentages, typically water vapor is just not going to be included just because water is going to change more drastically than the rest of these will. So you think about a dry day versus a humid day, we're still going to see roughly the same amounts of the rest of these, but the amount of water vapor in the atmosphere in that case is going to be drastically different. So typically we don't include water vapor in these types of percentages. But what I also want to point out is going to be looking at the percent by volume and then the mole fraction. You'll see that these values are the exact same. It's just with percentage, we're thinking out of 100, so 0 to 100. With mole fraction, we're thinking about 0 to 1. So we're just moving that decimal over 2, so 78.08 to 0.7808. But with this, we can see that it doesn't really matter what the gas is. The percent volume and the mole fraction are going to be the same. Just a factor of 2, or an order of magnitude of 2, excuse me. Factor of 100. And with it, that's going to make some of the calculations we'll see later on. Not in this section, or not in this video, I should say. But some of the calculations we'll see later on are going to be easier because a lot of the times we're not going to need to consider what gas we're dealing with. because we're going to essentially be able to treat all of them the same. It's just going to be the conditions with which that gas is experiencing is going to be the important piece. And with it, we'll see in the next chapter, we'll talk about liquids and solids. We'll talk about the intermolecular forces and how those kind of influence the properties of different substances. But with gases, we have them separate. And it's going to be because with the gases, there's essentially no intermolecular force. So if you think about a solid or a liquid, those molecules or atoms are going to be pretty close together. There's going to be an attraction between them. But now with the gases, because we've given them more energy, we've heated them up, we're separating out those molecules now. And because of that, like I said, there's essentially no interaction between those different atoms. And that's why these gases expand to completely fill the entire volume, entire shape of whatever container they're in. And then because of that, we're going to see that they're highly compressible, meaning that the volume is going to change with pressure. Whereas solids and liquids, in some cases, they might be very, very minorly compressible. So there may be very, very minor changes with pressure. But for the most part, we're not going to see solids and liquids change with pressure. But with gases, we just think about a balloon. You squeeze a balloon, we're increasing the pressure. And then, of course, that balloon gets smaller. So that's why these are going to be compressible, just meaning that it's going to essentially change with pressure. And then with these last 2 points, these are kind of just general. Of course, there are different gases that are going to have much different densities. Typically, they're going to be pretty low. But if you think about helium, I'm sure you've probably seen videos, at least, if not in real life. Somebody inhales helium, and then their voice gets much, much higher. The exact same thing occurs with sulfur hexafluoride, so SF6, just the opposite, because sulfur hexafluoride is going to be much, much denser than helium. So it actually lowers your voice. So you get a much deeper voice if you're actually to inhale sulfur hexafluoride. So we can have different densities, and then of course that's going to affect how well they mix. If we had just a room full of sulfur hexafluoride and helium, they're not really going to mix well. Helium is going to float to the top. Sulfur hexafluoride is going to sink to the bottom. But for the most part, if we're thinking about the atmosphere, the air that we're breathing in, for the most part, we're going to say that they're mixed pretty well. And then in addition to these gases being affected by pressure, we're also going to talk about volume, which is going to be just kind of the opposite of pressure. We're going to see those are inversely related. And then temperature is going to be directly related to pressure. But we'll see all three of these factors are going to affect how a gas sample behaves and what the other properties of that sample will be. So when we think about air pressure, essentially what we're thinking about is just the amount of force that air is exerting on something. So when we think about just atmospheric air pressure, we're essentially just thinking about if we took all of the air in a small column going all the way up from the surface to the top of the atmosphere, how much force from gravity is that air pushing down with? And with it, I like to think about if you were swimming, if you were diving in water, as you go further and further down, the water pressure increases. So think about what was the name of I can't remember the name of that like little poorly made sub that was trying to get to the Titanic that imploded. The reason it imploded is because as it went further and further down, the amount of pressure from the water pushing on that submersible increased and increased just because there's more and more water above it now. It's kind of the same thing with this air pressure. We're just having a much, much smaller amount of pressure just because it's air versus the water, but it's a very similar idea. And with pressure just in general, we've got some force applied over an area. So again, you can see a little bit better here what I meant by the column of the atmosphere. Just thinking about all the air above us, how much force is it pushing down? But then with it, if you think about it, if we have a column like this, it's covering some amount of area at the surface here. Whereas if we had a column that took up the entire continental United States, the amount of force that's pushing down with is going to be much greater than what we see with this column. But also the amount of area that's covering is going to be much, much greater. So the pressure would more or less be the same. And with it, one example we can use to kind of understand this is if we think about an elephant versus an ice skater. So of course, the elephant's going to be much, much larger. It's going to be pushing down with much, much force as it takes any of its steps. But then if you think about the size of the elephant's foot, going to be relatively large. So that force is going to be spread out over a relatively large area. Whereas the ice skater, it's going to be a much smaller force because they're a much smaller person compared to the size of an elephant. But now if you think about the figure skating blade here, it's going to be very, very thin. So even though we've got much less force, we've got it spread out over much, much less area. So what we would actually see in this case is the amount of pressure on this ice skate would actually be much greater than the pressure on the foot of the elephant, just because the area difference is also going to have an impact. So when we think about gases, if we think about a balloon again, the pressure within this balloon is just going to be the force coming from the gas molecules inside. So they're going to be constantly moving, just hitting the balloon itself. And then it's going to be divided by the amount of area we have here. So if you think about it, if we have some amount of force, but then we make this balloon twice as large, now it's going to be spread out over more area. So that pressure is going to decrease. Whereas if we keep the amount of force the same, but can make that balloon smaller, now it's going to be much, much more pressurized because it's going to be applying that force to a smaller area. So we've got to consider both of those pieces when we're thinking about pressure. And with pressure, we'll see we're primarily going to be using the unit of atmosphere, but there are a whole bunch of different pressure units. So if you think about if you drive a car, for instance, or even just ride a bike, when you're filling up the tires on either of those, typically there's going to be within cars, usually there's like a sticker on the driver's side door. With bikes, there might be a similar sticker somewhere, but it's telling us what the recommended tire pressure is. And typically that's going to be in PSI, so pounds per square inch. So if you think about the unit for pressure here, PSI, pounds per square inch. Pound would be the force unit, and then per square inch, that square inch is going to be the area. So if we had a tire for a car that was at 36 pounds per square inch, it's 36 PSI. That means for every square inch of tire, it's going to be pushing, it's going to be exerting 36 pounds of force. And with any of these units, that's going to be what we're measuring still. It's just the pressure of that force over a given area. But we have to have a whole bunch of different units we can use for it. Like I said, primarily, we'll be using atmosphere. But there are what's known as torr. And then torr is also going to be just the same thing as a millimeter of mercury. And with this atmosphere unit first, before we look at the column here on the right, the atmosphere is essentially just thinking it, if we were at sea level, then you'd have one full atmosphere of air above you. So the amount of pressure pushing down on you would be one atmosphere. And then if you think about it, if you've ever gotten higher in the mountains, if you tried to boil water, it's going to boil at a lower temperature than 100 degrees C, just because there's going to be less pressure. So if you think about going higher in the mountains, now there's less atmosphere above you. So it's going to be pushing down with less force. We'd have a lower pressure there, so we'd have less than one atmosphere of pressure. And with this, again, remember, like if you think about meteorology, we do have high and low pressure systems. So it's not always perfectly one atmosphere of pressure at sea level, or any location. We're going to see it's going to change. But that's just where the one atmosphere comes from. It's just kind of the average air pressure at sea level. But then on the right here, we've got what's known as a mercury barometer. So barometer is just a instrument for measuring pressure. And in this case, we use a mercury barometer, or we call it a mercury barometer because it's filled with mercury here. But essentially, we've got kind of two pieces. At the bottom here, we've just got a pool of mercury. So remember, periodic table, we've got two elements that are liquids at standard conditions. Mercury, going to be the one metal. Bromine, going to be the one non-metal. But we've got this pool of mercury at the bottom, and then we've got a very thin column or a very thin tube. And what we're going to see is as this pressure, as this atmospheric air pressure increases or decreases, it's going to be pushing down on this pool of mercury with more or less force. So if we think about as the pressure increases, now we're going to have more force pushing down on this pool of mercury. And as it gets pushed down, some of it's going to be forced into this tube. It's actually going to get pushed higher into the tube. So what we can do, is just measure the height of this column of mercury. And that's why we simply just often refer to it as millimeters of mercury. We're just counting or measuring the amount of millimeters that this mercury goes up into the tube. So the higher the number, the more pressure there is, because the higher that mercury was pushed. And with it, it makes it a little bit easy, because 1 millimeter of mercury is going to be equal to 1 torr. So if we wanted to, we could have 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters of mercury. Sometimes you'll see inches of mercury. I think we'll see that coming up in a second. But millimeters is the more common one. Remember, in science, we use the metric system much more than we use the English imperial system. So we would not really use inches for anything in this course. But like I said, typically, we're going to be using atmosphere. And then we saw on the previous slide, 1 atmosphere going to be equal to 760 torr, or 760 millimeters of mercury, same thing. And then another common unit is going to be kilopascals. So we can see 1 atmosphere is equal to 760 torr, which is equal to 101.325 kilopascals. But again, in each case, these are just measuring how much force, how much pressure is being applied by that gas sample, or the atmosphere, if we're thinking about it like that. And then we can just see a whole bunch of other units here. So atmosphere, kilopascal, millimeter of mercury, torr, PSI, like I mentioned at the bottom before. And with it, you'll never have to memorize these conversions. On a quiz or a test, I'll either give you these in a table, or for a given question, I'll give you whatever conversions you may need there. But on the next slide, we're going to have a question that kind of requires you to just convert pressure units. So starting in, what is it, inches of mercury. Actually, yeah. So what I would recommend you do is, with this one, just write down 29.2 inches of mercury. And then let me, inches to millimeters. All right. So have you practice on your own, but you'll want to write this down if you're going to practice on your own. 1 inch is equal to 25.4 millimeters. All right. And the reason I would recommend you write this down is because then you can just go back to the previous slide, look at the conversions we had here. It's just on that table. We didn't have anything with inches of mercury. So first we'd have to get to millimeters. So you'll want to use this as our first conversion factor to go from inches of mercury to millimeters of mercury. And then what I would recommend you do is look here. All of these are related to atmosphere. So what I recommend you do is actually solve for B first. So go from inches of mercury to millimeters of mercury. And actually, remember, millimeters of mercury and torr are the same. So you really could do the first one first and then convert to atmospheres. But then we can convert from atmospheres to kilopascals, or atmospheres to millibars. So if you want to practice with that one on your own, just pause the video, give yourself a chance to kind of go through that. And again, you want to look back at that previous slide so you have the different conversions there. But I'm just going to erase this so we can start moving ahead. But like I said, first we got to go inches of mercury to millimeters of mercury. Then for millimeters of mercury to torr, it's just going to be that same value. We're just going to change the unit, because 760 torr is equal to 760 millimeters of mercury. Then we can convert to 1 atmosphere, just divided by 760. And then using the atmosphere, we can then get kilopascals in one step. We can then get millibars in one step. So just seeing the process there. So like I said, 29.2 inches of mercury. So in this case, we can see the units already crossed out. But 1 inch is equal to 25.4 millimeters of mercury. So if we stop there, we'll just get 742 millimeters of mercury. But we want to go to torr, just a 1-to-1 relationship. So that's why we don't have to change the unit at all. And then to get to atmospheres, we can essentially just add on to that step. So 760 torr is equal to 1 atmosphere. So that's why we're dividing here. Torr cancels. We're left with ATM. And with this, we can always think about it if that makes sense. So 760 torr is equal to 1 atmosphere. So if we have 742 torr, a little bit less than 760, so it makes sense that we're just a little bit under 1 atmosphere there. And then for the rest of these last two, I would really just take this step, since our conversions on the previous slide were all related to atmosphere. So I would do 0.976 atmospheres, and then 1 atmosphere on the bottom, 101.325 kilopascals on top to get just under 99 kilopascals, and then do the same thing kind of with millibars just to get just under 1,000 millibars there. But again, we're just using the relationship from the table with those different conversions. We don't need to memorize those at all. Any conversion that we're going to need will be given to you on a quiz or test. You're just going to have to know, kind of like we see here, how can we use those conversions to go from something like torr to atmosphere, or kilopascals to millibar, whatever it may be for those different units. And then with the barometer, just to talk about that for one more second. Like I said, mercury barometer, millimeters of mercury, inches of mercury sometimes. But with mercury itself, going to be a toxic substance, something we don't want to expose ourselves to. That's why typically even thermometers are no longer mercury. There's some type of, I think it's an alcohol-based substance that has like a red dye added to it. But mercury is going to be a nasty substance, depending on what form it's in, because it can be inorganic or methyl mercury, elemental. So there's a couple different forms of it, determines the exact toxicity, but none of them are great. So we've got to think about, why do we use a mercury barometer? And the reason for it is simply just going to be essentially the ease of it. So we could set up a barometer with water, would work exactly the same, just kind of have a pool of water, big tube for the water to go up. But because mercury is going to be much, much more dense than the water will be, water is going to go much, much higher with the same amount of pressure being applied to it. So we would just need a much, much larger barometer. So if we think about mercury versus water here, again, atmospheric pressure in each case. So we've got 1 atmosphere of pressure pushing down on these pools of liquid. But because the mercury is so dense, 1 atmosphere of pressure is only going to cause it to go up 760 millimeters, which is just about 2.5 feet. Whereas that same amount of pressure is going to cause water to go up nearly 34 feet. So we would just need a lot more space. It's just not going to be really feasible in most circumstances to use something like water. Additionally, water, you do have a little bit of the ability to evaporate, or at least more easily evaporate than mercury. So there may be other considerations there if you're in a warmer area. But generally, just going to be because of the size that would require. All right, and then with the barometers, which are just measuring the air pressure itself, they don't need to be the types of column barometers like we just saw in the lab room, for instance. There's just kind of a gauge on the wall with a needle that just moves back and forth as the pressure increases or decreases. And then it's got a couple different measurements reading. So you can do like atmospheres, torr, and kilopascals maybe, or something else at the same time, depending on what unit you may need for a particular reason. But in addition to the barometers, we've got what are known as manometers. And essentially those, instead of measuring the atmospheric pressure itself, those are going to allow us to measure the pressure of a system, or the difference in pressure. And there's going to be 2 different versions of it. So the one we can see here is what's known as an open-ended manometer. And the reason for that is just because, like the name would suggest, the end of it is open to the atmosphere. But the way this works is we've got a reaction vessel, or just some gas sample. And then we've got a tube filled with mercury still. So depending on the pressure of the gas, depending on the pressure of the atmosphere, those are going to force this mercury to move one way or the other. And then depending on which direction it is pushing more, allows us to determine the pressure of the sample here. Because if you think about it, if each of these were the same, so if the pressure of the atmosphere was equal to the pressure of the gas, each of them would be pushing on the ends of the mercury with the same amount of pressure. So they would just wind up being equal. Both sides of this column would be at the same height. So the pressure of the gas would be equal to the pressure of the atmosphere. But in this case, we can see that the mercury goes up higher on the atmosphere side. And what that's telling us is that the pressure that this gas sample is exerting on the mercury is greater than the pressure that the atmosphere is exerting. That's why we're getting it pushed further in that direction. There's more pressure on this side. So what we can do is use the equation at the bottom. So the pressure of the gas, pressure in this vessel, is going to be equal to the pressure of the atmosphere plus the pressure reading that we make here. So again, just like with the barometer, or the mercury barometer at least, we can just measure the height difference here. And that'll be our pressure in millimeters of mercury or whatever distance unit we use to measure, but typically millimeters. And then just conversely, if we had more pressure in the atmosphere, I think we'll actually see that right here. Yep. Now, if we have a greater atmospheric pressure, we have more pressure on this side, pushes the mercury further to the left, and we would just see a situation like this. But again, we can measure the difference in the pressure here. It's just going back to this equation. We're essentially going to be subtracting that one in this case because we want a negative pressure difference at least. And then the other version of these, just closed-ended manometers. And the reason we've got the difference here is the open-ended manometers typically going to have pressures of around 1 atmosphere. So if you think about the atmospheric pressure here, if it's much greater in the vessel than 1 atmosphere, we're going to have a lot more force on this side. We're actually going to shoot that mercury out of the column. And then similarly, but kind of the inverse, if we've got much smaller pressure, much less pressure than 1 atmosphere in this vessel, now the atmospheric pressure going to be pushing with much more pressure, going to force the mercury all the way up that column and into the vessel itself. So with the open-ended manometers, we're looking at about 1 atmosphere of pressure in the vessel, plus or minus a little bit, but it's going to be pretty close to 1 atmosphere. Whereas the closed-ended ones, those ones we're going to be looking at very low pressure to begin. So that's why we've got the closed-ended ones so that we can actually measure those lowly pressurized systems. Right. So if we look at a question here, we've got a closed-ended manometer. The pressure of a sample of gas is measured with a closed-ended manometer as shown to the right. The liquid in the manometer is mercury, determining the pressure of gas in torr, in pascals, and in bars. So the first thing we need to do is look at this height and see that it's getting pushed to the right. So we've got a pressure of 26.4 centimeters of mercury. But if we want torr, we need to remember torr is millimeters of mercury. So we can essentially move that decimal over 1. So we'd have 264 millimeters of mercury or 264 torr. And now if you want to use some of the conversions we've already had to try to get 264 torr to Pascal or 264 torr to bar, just pause the video. But just like with the previous ones, we're just going to use those conversion factors, just manipulate the units. It's just in this case, we've got to recognize that the pressure we're going to start with isn't coming from the question like the previous one. In this case, or at least not directly from the question, in this case, we've got to determine what that pressure is going to be ourselves. So that's where the 26.4 centimeters comes from. But like I said, with the first one, essentially just moving that decimal over, because centimeters to millimeters is a 1 to 10 relationship, and then millimeters of mercury to torr is just 1 to 1. And then for the pascals, got to do a couple conversions. So 760 torr is equal to 1 atmosphere. If we stop at that point, we'd have atmospheres of pressure. And with it, it should be a little bit over 0.3, just because 264 is a little bit over 1/3 of 760. But we're going to pascals, so now we're going to multiply by 101,325 and get 35,200. And then for the bar, we can see 1,000 pascals is equal to 1 bar. So now we're just dividing by 1,000, converting those units, just getting 0.352. And then with these, again, remember, we're always paying attention to sig figs. So we've got 3 sig figs in the initial pressure, 26.4 centimeters of mercury. So that's why we've got 3 sig figs in torr, 3 sig figs in pascal, 3 sig figs in bar. All right. And with the closed-ended ones, I think those are a little bit easier just because there's not really any other piece to consider at all. Just how much does the mercury go up, basically. But now with the open-ended ones, we're kind of doing the same thing. But now we've got to also remember, since this end is open to the atmosphere. It's experiencing the pressure from the atmosphere. So now we've got the 13.7 centimeters of mercury just from the tube. But then we're also looking at measured at sea level. So we're going to assume there's 1 atmosphere of pressure as well. So we're going to assume there's 1 atmosphere of pressure pushing on this end. So in addition to the 13.7, we've got 1 full atmosphere of pressure on the left-hand side here. So when we're first starting, again, we've got to figure out centimeters to millimeters. But we need to include not just 13.7, we need to include that full atmosphere of pressure that it's also exerting, because we've got that open-ended manometer in this case. So with this one, let's see if I insert text box. This one I'll show how we can actually do rather than just use the all right. So for this one, if we think about pressure of gas is equal to P height plus P atmosphere. I guess I can actually let me do that with the subscript so it's not as messy. Just to make it clear why I was saying we have to include the atmosphere pressure rather than just the 13.7 is, remember, with this type of setup, we've got the pressure of the gas being equal to the atmospheric pressure plus the pressure from the column, or at least the measurement we get from the column. So now when we look at this, P gas atmosphere pressure, we'll say is 1 atmosphere plus 13.7 centimeters of mercury. So with it, we've got to convert these units. They don't match up at all. We can't add atmospheres and centimeters of mercury directly. We need to get those to be equivalent in order to add them. So again, remember height. If somebody's 6'4", we can't just add those together and get a height of 10 something. We've got to convert either the 4 inches to feet, or we've got to convert 6 feet to inches and then add them. The same idea with any of these units. So atmospheres and centimeters of mercury don't match up. But what we can do is use our conversions. So 1 atmosphere is equal to 760 millimeters of mercury, and then 1 centimeter is equal to 10 millimeters. So we'll wind up with 760 millimeters of mercury. We'll wind up with 137 millimeters of mercury. So ultimately, we'll wind up with 897 millimeters of mercury there. And that's the first piece. But now we want to convert to atmospheres. We want to convert to kilopascals. So that's just going to be where we use those other conversions. And with this one, we've already got it kind of here. So 760 millimeters of mercury is equal to 1 atmosphere. But we've got almost 900 millimeters of mercury. So when we convert this to atmospheres, we should get a value larger than 1 atmosphere. So at least just kind of think about these values. Think about if these numbers make sense as you're going through these conversions. Because because now if we convert 897 millimeters of mercury to the value of atmospheres, and we get a decimal less than 1, that means we probably just had something set up wrong. We might need to flip our conversion or whatever. Or if we get a value much, much greater than 1, then we probably multiplied when we should have divided. So we can at least use that to think about the context of these values, if they make sense at all. But for the other two here, we'll just use the conversions. So again, 760, so we should wind up with 1.18 atmospheres there. And then for the kilopascals, got a little bit over 101 kilopascals for every atmosphere. So we're going to wind up with a pretty big number in that case. And with it, so I took this from the textbook. I'm just realizing now that they wrote it in scientific notation. So this is really just 120 kilopascals. But they're just doing that so we can represent the 3 sig figs there. And then with this pressure, like I said, we'll see different applications of it, especially when we start to look at the relationship between pressure and temperature, pressure and volume, volume and temperature, amount of gas, and all of these other things. But I just included this in there so we can see that some of the applications of pressure. Thinking about blood pressure, of course, so it's an important thing to monitor. High blood pressure, I think, is often a indicator that there may be other issues going on. So typically, at least when you go to the doctor, they always check that, but it's a good thing to keep track of yourself. But that's going to be utilizing pressure. And then with the meteorology that I mentioned earlier, so we've got high and low pressure systems had different indications or implications, I should say, in terms of like the forecast coming up. So that's why you'll often see these types of measurements here. With it, I haven't thought about this before, but now I'm seeing these 1,000 numbers. And what I would guess is what these probably are is millibar, maybe, pressure units in millibar. I didn't think about that. Let's go back here a second. Yeah, so when you look at all these, you can see 14.7, a little over 1,000, a little over 1, 760, 101. So this is a real big number in just pascals. So the only one that's really close to any of those is millibar, so 1,013. I hadn't thought about this before. So let's see. And now you can see a high pressure system. It's about 20 over that. A low pressure system, just a little bit under. You can see up here a little bit lower even still. So I've never actually thought about what these units are, but now actually looking at them, I would be pretty confident that these values are the pressure of the atmosphere in millibars at these areas. So you can see, again, not constant, so we do have those fluctuations, but they're all about the same value, and that's why we just kind of use that as the average sea level pressure. It's just that 1 atmosphere pressure, or 1,013 millibar. You can see they're all kind of around that value. But with the rest of the section, we'll start to look a lot more at the relationship between these different properties. So pressure, volume, temperature, amount of gas, things like that, as well as different kind of real world applications of those. So we'll actually have a whole bunch of different rules or different laws for the relationship between these. And ultimately, we'll be able to kind of combine them into what's known as the combined gas law. And then we'll also have the ideal gas law. We'll start to go through that in these later videos.